And so apologies for last week. So there was no electricity for 2 days where I live in Los Angeles, and I didn't manage to arrange a way to give the talk somewhere with electricity. It was too complicated. So I'm sorry. So today I will be trying to tell you about representations of Quiver Hecke algebras. So this is meant to be somehow a preparation, an introduction to some topics leading to a talk by Peng Chan next week. So some beautiful work of joint work she did with Michela Varagnolo and Eric Basro. So what I will be discussing has to do with complex semi-simple algebras, or if you want Kac-Moody algebras in general. And what she will be discussing is something which has to do with affinization of this picture. So various people have been trying to do things in this direction for some time already. But so their work is first somehow structure theorem involving maps in those categories, or involving Quiver Hecke algebras and affine versions of them for SL2. So my talk will be about the classical theory, and so I will try to use as a reference Lustig's work on quantum groups and the various bases in quantum groups. So Lustig constructed 4 bases in the positive part of a quantum group, and that's something unusual somehow in representation theory. Typically, you would have 3 bases, say something corresponding to simple, something corresponding to indecomposable projective, and something corresponding to standard modules, or whatever, Verma or Val modules. So there are 2 kinds of standard modules. There are 2 kinds of standard basis, of PBW basis for quantum groups. And so that's not very complicated. That's fairly easy to see from the point of, from the quantum group point of view, it's no big deal. From the Quiver Hecke algebra point of view, it's a slightly more delicate matter. And from the point of view of geometry, in some sense, that has to do with looking at equivalent or non-equivalent objects. But there is a difficulty in the geometry in that it's difficult to see both at the same time. So it's usually not a good idea to think of an object somehow from a non-equivalent category as coming from an object, as having to do with an object of an equivalent category. So I'll try to keep things algebraic at the beginning, and then I will bring a little bit of geometry in the second part. So if there is something, please stop me for questions. And also, if for some reason my internet connection is not so good, please alert me. Okay, I might not realize that. So I will start with a case which is somewhat crucial, the case of SL2. So from the point of view of Quiver Hecke algebras, this has to do with nil affine Hecke algebras of GLN. So it's the theory is very easy in some sense in that case, but it's also a good illustration of the general theory. So I will be working over a field of characteristic 0 always. Many things generalize, but the geometrical part, some aspect, canonical basis, etc., does not. And so what is this nil affine Hecke algebra of GLN? Well, it's an affine Hecke algebra, so it's not really, it's an extended version of the one you would think of as associated to a Coxeter group, to the affine symmetry group. So let me give it by generator notation. So Hn is generated by variables x1, xn, then Ti's, And so the xi's commute. And the ti's satisfy Haber relation, symmetric group equations. So ti tj is tj ti if I and j are not too close. We have a braid relation. And so it's called the nil algebra because we are setting, so if you think of Hecke algebra with two parameters, we're setting both parameters to 0. Okay, so the top, so xi's will generate polynomial algebra. The ti's will generate a Hecke algebra of the symmetric group, and the interaction between them is non-trivial. So there is commutation if j is not I or I plus 1. And otherwise, there is some more semi-classical limit of the affine Hecke algebra relation. Okay, so that's a type of algebra that would generalize to any finite value group and being used by particular by Lustig a lot, and it's sometimes Lustig called, well, not for TS square equals 0, sorry, it's version where TS square is 1 would be what Lustig has used. So what do we want to say? Yes, the as a vector space, Hn splits as a tensor product. Where this is say the nil Hecke algebra of the symmetry group, and that as vector spaces. Okay, the two subalgebras K of x1 xn and Hnf are subalgebras, but they don't commute. Right. So now this algebra is graded by taking xi's of degree 2 and ti's of degree -2. That makes the relations homogeneous. This algebra has a very simple structure. So you can see that by introducing a certain idempotent. So you take for Bn, so W0, the corresponding T, where W0 is the longest element of Sn, and you multiply that by a monomial. So that's an idempotent. And it's even a primitive idempotent, and the corresponding module Pn is a projective. That's clear, but it's an indecomposable Hn module. And what you find, so I'm not focusing on the grading, I'll talk of the gradings a little bit later, is that the algebra the Hn itself is isomorphic to a certain number of copies of that module. N factorial copy as a Hn module. Right, so that's telling you basically everything you might want to know about projective modules for Pn. There's a unique projective indecomposable module up to isomorphism. And what about simple modules? Well, you can't quite make this algebra acts on the field. You have to induce somehow from the polynomial well, let me write down what it is. So maybe I should tell you what is the structure first, because you see Pn now, sorry, what I call Pn is a progenerator for Hn. So it's a projective module, and every module is a direct summand of a multiple of that one. That implies that Hn is Morita equivalent to the homomorphisms of Pn. So that's Hn, Bn, Hn, and that's, you can see, is invariant polynomials. So it's a classical fact, and this Pn can be identified itself with polynomials in the variable x1, xn, and the actions of Ti's on that are by BGG de Mazur operators. And so that's because the Hn is n factorial copies of that, that will tell you that Hn is actually as an algebra, a matrix algebra of rank n factorial over symmetric polynomials. Okay, so we have a matrix algebra over a polynomial ring. So it's not so interesting from the point of view of representation theory. So matrix algebra is a unique simple module. At least if you think of graded modules. So there's a unique, say, simple graded module. Let's say up to shift, up to grading shift. Let's go maybe ln. So you can take K as a unique graded modules over the ring of invariant polynomials, and you can just tensor by your module Pn, and that does the Morita equivalence. So this is, you can write it as a let's say Pn tensor over x1 xn. So going back, okay. Okay, so I mean, you can write that as a coinvariant. Pn is a free kx1 xn module, fixed by Sn of rank 1. So this is modulo. So you take the invariance of positive degree, and you take the ideal generator, the usual coinvariant ring. This is the size of this module Ln. It's the only one on which the X size will be nilpotent in this simple module. And up to shift, I mean, you have to set some, decide which degree you put, in which degree you put a generator. So it's a good idea to see, when you look at symmetry groups or Hecke algebras, to look them for all n's together. And the one for n embeds in the one for n plus 1, or more generally, tensor product of the one for n by the one for m embeds in the one for n plus m. And you can encode all that structure into a monoidal category. So let me call it maybe U plus, where the object I will call e to the n, where n is greater than or equal 0. So the tensor product is just adding up the indices, and we put om en to be 0 if n is not m, and otherwise we put our nil affine Hecke algebra. So we need to give a structure of, we need to explain how we take tensor products of maps, and that's given by the embedding of a tensor product of two Hecke algebra in a bigger one. So why do I want to talk about the monoidal category point of view? Well, it's, for example, convenient to view things from the point of view of generator and relation. So U plus is generated by one object as a monoidal category E. Okay, so you take E and you take the powers of E, and by one arrow, by two arrows, X, which will be a map from E to E, and what I say T, from E tensor E, which I will rewrite as E square, from E square to itself. Okay, I'll stop writing the tensor product. I'll write the tensor sign. I will write the tensor products as just ordinary products. And modulo, so generated by these. And what about the relations? Well, there are certain relations. okay, let me not write them. So how do you recover the full nil affine Hecke algebras from those? Well, xi is acts on once you have this x and the t. So if you write e to the n, if you decompose it as e to the n minus I, e to the I minus 1, so this tensor product of 3 terms, so you can define a map where you put the identity x and the identity. This is an endomorphism of e to the n. You're only using x, but you're putting it at whichever position you want. And so there are n possibilities. You get your n variables. And ti acts. So you do something similar, except that you put an e square. And somehow, for example, the commutation between xi and xj is automatic in your modular category. The commutation between ti and xj when I is not too close to j is also automatic. And so the only relations you need to impose are Bread relations, ti squared to 0, and the interaction between xi's and xi and ti and xi plus 1 and ti. That's the only relations you need to impose. Right. So now we can look at so this modular category, it's Grothendieck group, something we can look at. So what I really want to do is look not just at U plus, but also at what you call the idempotent additive idempotent closure. So you allow direct sums and direct summands. So one way to think of that is to look at let's say you look at graded modules, projective. So for me, that will mean the direct sum of projective graded modules, finitely generated graded projective Hessian modules. So that's a definition, and this category is being graded. Its Grothendieck group is going to be a module over Laurent polynomials in one variable. So K0 Q is going to be a shift of grading. And it's also an algebra. It's actually, we have a tensor product on our category, and that gives a Grothendieck group that makes it into a module. So, well, we have a basis. I mean, it's not difficult. It has a basis because we have said that there is a unique projective indecomposable module. So when you look at graded versions, it's unique up to shift. And so we take the class of that projective module. So it's a vector space with such a basis. And so what is the class of Pn? Well, the class of Pn, so let me see what else I want to say. Yeah, the class of P. So let me maybe right away say something else, is that this is as an algebra, this is Lustig's integral form of the positive part of the quantum group associated to SL2. Okay, so so you would have as a quantum group you have if you look and see Q, you have a polynomial ring in one variable, and inside So I should say, let me call the integral form like that. Inside, you can take the z of q plus or minus 1 subalgebra generated by the divided powers. So q divided powers, where q divided power is defined like this. Okay, so these e to the n do actually, I mean, this is already, this is closed under multiplication. So it's not just generated by these divided powers, it's really the basis of this of Lustig's integral form. So, so the e to the n forms that Lustig calls the canonical basis. So they are not exactly the same as our modules. So the canonical basis is something that's chosen to satisfy a certain self-duality property. And our modules Pn will need some shifting graded to be self-dual. So I will ignore later. I will ignore those shifts. Hopefully, I will remind you that I'm ignoring them. So this is not exactly the class of Pn. It should be a power of q times this corresponds to that. So so I say that I will ignore q to some power later. So these are important shifts, okay, but they are not so important for what I will be discussing. So now Lustig has introduced also a dual canonical basis. So there is so if you look at enveloping algebras of complex semi-simple algebras, or even the positive part, these are Hopf algebras, which are not commutative, but they are co-commutative. Once you quantize, they are neither commutative nor co-commutative. So I won't discuss the coproduct here, but an important fact is that they are actually self-dual as Hopf algebras, at least in the non-integral version. And that leads to all sorts of the fact that you have two versions somehow of all bases. So you have also a dual canonical basis. So, and this has to do with simple modules. So the dual canonical basis of Lustig is given by the power of q. So Lustig's I'm sorry, this is 1 minus 2 square q square to the n en, e to the n. And it's some power of q times the class of our ln. Okay, so you can look at the formula I gave for the simple module ln. So it differs from Pn by the graded dimension of the invariant ring. The graded dimension of the invariant ring is 1 minus q squared to the power n. Well, that would be if it was not the invariant ring. The difference between the two is precisely the n factorial. And so somehow we have this formula on one hand, and to get the simple compared to getting this Pn, sorry, to this Pn, you can see the differences is that up to power of q. Okay, so we are in a typical situation where we have a canonical basis, dual canonical basis. One is realized as projectives, projective indecomposable, one as simple modules. And now I will explain how that generalizes to arbitrary Kac-Moody algebras, say. So I'll now go to Quiver Hecke algebras. So to define the a Kac-Moody algebra, you start with a generalized Cartan matrix, which is symmetrizable. So here I will be dealing only with a symmetric case. So symmetric Cartan matrix can be encoded in is the same as the encoding of a graph. And so here we'll start with more than a graph. We'll start with a quiver. Let's say I will be the vertex set, and we assume there are no loops. And so we have a Cartan matrix, which is given by the number of minus the number of edges. So we forget the orientation. So that's for I not equal to j, of course. So that makes a symmetric matrix. So in the theory of Quiver Hecke algebras, there's some sort of polynomial version of the Cartan matrix. So you can choose something. There's a parameter space, and the geometry provides a specific point in that space. So there's this slightly strange polynomial that is not something you need to guess, but something that's provided by the geometry. So I define a polynomial in two variables. Which is essentially encoded by the graph, underlying graph of the quiver. So it's u minus v to the power number of edges between I and j, except that there is a sign. So the dependence on the orientation is just by a sign, and we put qi to be 0. So now we can define u plus a strict monoidal category, say over k. So home spaces are going to be vector spaces over k. So the generating objects are going to be parameterized by our set I. We call them EI. And now the generating maps, it's the same as before. We have maps which we can call X or Xi. Let me call them X from EI to EI. And then the map, we could call it tau ij from EI tensor ej to ej tensor EI. So we have now a monoidal category where the objects are tensor products of EIs, and we have maps that we can place wherever we want when we have a tensor product. And there are certain relations. So the first relation is the analog of t square equals 0. And it will be that if we do EIJ, so we apply our tau twice, so it's a different tau. This should be it's going to be 0 if I is j. But this composition in general will be, so that's an endomorphism of EI tensor EJ. And it's given by a polynomial. So you have an x acting on EI, an x acting on EJ, and you can take any polynomial function of those two variables. And the polynomial we take is QJI. That's where the polynomials enter. So we take the identity of EI, which I call EI still, EIX and XEJ. Okay. So we can act on EIJ by putting the x either on EI or on EJ. That gives us two commuting endomorphisms of EIJ, and we take a polynomial functions of them. So that's the first relation. We have another relation which is let me write where it takes place in endomorphism of homomorphism from EIJ to EJEI. So we have a map tau that goes from one to the other. We have also polynomials acting on polynomials in two variables, and there is a certain compatibility, which is direct generalization of what we've seen in the first part. Okay, so when I is not j, polynomials and tau commute, x's and tau commute. When I is j, this is the relation we've seen already involving EI tensor EI. And the final relation is the analog of the bread relation. And this is actually the most complicated relation because it's a deformed bread relation. It's not quite a bread relation. So if we take the product of three terms, and if we switch some of the first and the third term, which we can do using breading. So I have a question about EIX. Yes, this means identity on EI times X on EJ. Yes, thanks for the question. Yeah. Okay, so we have a version of the bread relation. So we apply bread. We apply this. Oops. We switch the terms in one way or in the other way. So the yeah. And so what we can do is apply X on the first position or in the second position, and then we do nothing on the last position, or we do okay, so we have three endomorphisms of EI, EJ, EI, which is X put in either of the three positions. And we take a polynomial of those three endomorphisms. And this polynomial I write as a fraction because it's easier, but it's really a polynomial. Okay, so a quotient of polynomial Qij, etc. I mean, this you can check is a polynomial of the three variables. Okay. So we have like that defined monoidal category. So the objects are things like products, tensor products of EIs. And there are no homes if we take products where the number of terms is different. As before, because the tau and the X respect the number of terms. So now we can encode our structure in, can take the sum of all products with a given small n, and this is our Quiver Hecke algebra. It's the endomorphism of the sum for I1, IN in I of EIN. So I could have given directly the definition of the Quiver Hecke algebra without introducing this monoidal category. So the point is that it comes with a bunch of idempotents, which are, there is one for each family I1 up to IN, which will, from that point of view, correspond to projecting onto a given summand of this direct sum of products. And then we have various x's and tau's that we can put in different positions. So you can do that. It's just, it gives a lot of indices. And the first thing I should say is that if gamma, if we look at this case, where gamma is a quiver with just one vertex, no arrows, then Hn of that quiver is the algebra we saw before, the nil affine algebra of GLN. And more generally, if we take a general I, Hn is the same as the endomorphisms of EI to the n. So that's back to the general case in general. Okay, so for EI to the n, the endomorphisms you get are exactly those. And so you can define something I didn't even explain before. You can define the divided power, if you want, of your, so there's a version of the divided power where you take the nth power of this object in your model category and you multiply by the idempotent we've seen before, so you can write it as EI to the n times Bn, where Bn was this idempotent, so that lives in cell completion. It's a little bit, we've taken a direct summand. We have an object EI to the n, we have an idempotent in its endomorphism ring. We can take the image of that idempotent, that's what I call multiplication by Bn. So that's not really in our category anymore, but if we extend our category by adding direct summands of objects, then then it's something well fine. So we have divided powers of our objects, and this category is graded, and the algebras are graded. So the x is still in degree 2, but the tau ij has a degree that is going to depend on I and j. And so if you remember in the case of we saw before SL2, with the case where I equals j here, we had degree -2, and in general, this will be the entry of the Cartan matrix. So one more thing I should say is that these algebras or the model category were defined using not just a graph. I mean, we had to use a quiver, and so up to isomorphism. This is independent of the orientation of gamma. So it depends only on the underlying graph up to isomorphism. But you have to be careful. I mean, this is not. This is something that is in certain aspects of the theory making things difficult, complicated, as we'll see. These orientations play a role in Lustig's work. So we have a big monoidal category. So we can look like as before. We can take the Grothendieck group of we can take graded modules, projective graded modules, which will mean taking the additive closure and then the idempotent completion of our category. Or if you want, we take projective graded modules for all n for the Quiver Hecke algebras, take the direct sum. We can do also modules, graded modules for each Hn of gamma, and take the direct sum of those. And this will coincide, and we have basis of simples or projectives there, and this will correspond with canonical basis, dual canonical basis, like we saw earlier. So state everything in just one theorem. So these algebras and the relation was something that was done independently by Kovanov and Lauda, and the canonical basis interpretation is something that I will say a little bit more after, is built on geometry, and something was done independently by Michela Varagnolo and Eric Bastro. So the theorem is that there is an isomorphism of algebras between Lustig's quantum group for the positive part. So gamma will give you, you have a Cartan matrix, symmetric Cartan matrix, generalized Cartan matrix. You can associate a Kac-Moody algebra. You can take the positive part, the part generated by EIs, and have a quantum version, the Lustig form of it. This is the same as K0 of what they call U plus, so graded projective modules. So for each Quiver Hecke algebra, and you take the sum of all ends. and you do that by just sending EI to the class of EI, which will mean you're taking H. You look at H1 of gamma, and H1 of gamma is just a direct sum of polynomial rings in one variable, and EI is one of those correspond to one of those polynomial rings. And so the canonical basis here will correspond to indecomposable projective modules. Again, they need to be put in suitable degree so that they're self-dual. Otherwise, you get the canonical basis elements up to the power of q. And similarly, with the dual canonical basis, which corresponds to simple modules. So there is there are those algebras, Hn of gamma, and you have maps from Hn, tensor Hm to Hn plus m, and you can use that as some sort of induction if you want. That gives a multiplication on the sum of k zeros of those Quiver Hecke algebras, and the algebra you get is the positive part of the quantum group, and you find interpretations of the canonical basis and the dual canonical basis. So that's explaining some of the interest in so simple module here are just simples, I should say, graded. Everything is graded there. So the simples are yeah, I'll say more. So simples, okay, I'm not sure I understand the question. So, but I'll say more about the specific objects one considers in relation with PBW bases. So the interest in Quiver Hecke algebras comes from the fact that they are describing maps in this category, which is a categorical version of the positive part of a Kac-Moody algebra. And so there are cases where it's not really new, and that's something that we had considered earlier with the Joe Schwang. It's a case where gamma is a cyclic quiver. So that G gamma is an affine algebra, SLI hat. In this case, representations, I mean, these Quiver Hecke algebras are certain completions of affine Hecke algebras. And so let me state a theorem, one version, which was something that was done apparently by Bodan and Kletchev, and which they used for some applications to graded decomposition numbers. So what does the theorem say? It says that if you look at modules over your Quiver Hecke algebras, which are, so we want to, so a simple module, if you start with the algebra H1 that we considered in the first part, it's a polynomial ring in one variable. So it has lots of simple modules. So those that are graded, there's only one that can be graded. It's the one where x acts by 0. So in general, we want to look at modules for Quiver Hecke algebras on which the xi's are locally nilpotent. Now, this is the same as going to be equivalent to modules over an affine Hecke algebra. So we can look at H affine of GLN. So it's almost the algebra. We saw a nil, some sort of degenerate version earlier. So it will be an algebra generated again by x1, xn, t1, tn minus 1. But we look at it at parameter q. So now it has its usual parameters, ti as parameter, ti plus 1, ti minus q is 0, and we take for q an is root of unity. And we look at modules there, such that where eigenvalues of x size are in the set, is the root of unity, or are the set. So if you look at a representation of affine Hecke algebras, the category of finite dimensional representation is going to split as a direct sum. Doesn't matter if Q is a root of unity or not. According to you look at eigenvalues of x size and you let them be in. If the eigenvalues of x size are not related by power of Q, the modules will be in different parts of the category. So you can always ensure that the x size act all by some scalar times the power of Q. So I'll be taking a break in a couple of minutes. Thank you. So this result tells you that in this affine type A case, you can somehow repackage this monoidal category to a large extent, or repackage these Quiver Hecke algebras. They are really given by affine Hecke algebras, and there is a grading. Where does that grading comes from? Well, it comes from using this x size. So from the point of view of symmetric groups, that would be Justice Murphy's elements, and looking at these algebras using those and a grading coming from those. So what's interesting from this result is that you can deduce from that group algebras of symmetric groups, or more generally cyclotomic Hecke algebras, are actually isomorphic to certain quotient of Quiver Hecke algebras called cyclotomic Quiver Hecke algebras. Okay. So that gives you grading on those more classical cyclotomic Hecke algebras. So it's a good point for me, yes, to take a break. So in the next part of my talk, I will be discussing representations of Quiver Hecke algebras and their relations with the bases of the quantum group.
All right, excellent. Thanks, Raphael. Yeah, if anybody has any questions, this is a good moment to chime in and ask away. We'll also have questions afterwards at the end, of course, or if you need a break.
Hi, Raphael. I've still been wondering about something. I don't know if anything's changed since the last time I asked this question years ago. How explicitly are the canonical bases known in terms of the PBW bases?
Wait, say it again. How explicit are the canonical basis elements?
Yeah, exactly. You know, for SL2, I know this formula.
Yes.
For SL3, I know this formula.
I mean, I don't know. I mean, people worked hard. I mean, there are certain elements that are, I mean, there are those, what is it called, tight monomials. I mean, there are certain, there was work of Lucic, Robert Marsh, and other people a while ago in the 90s, I think, identifying certain canonical basis elements in terms of the PBW basis. But as far as I know, there isn't more that's known. So there is there is an algorithm to compute. It's a purely combinatorial algorithm, but there isn't a closed formula. It's an iterative formula, so it's not. It's as good as it gets somehow in a Kazhdan-Lucic type situation, in some sense, or canonical basis. I mean, Lucic, Kazhdan-Lucic. So. There is no, so it's, I'll say one or two. I mean, from the point of view of representations of Quiver Hecke algebras, writing down explicitly simple modules like you would do, I don't know, for symmetric groups is something that has been done for finite type by a number of people, Kleshef, Bondam, Ram, McNamara, Cato, etc. But it is quite a bit of work, and this has not been extended to general type. So in some sense, your question, if you ask a question, relation, we don't even know how to, or say the standard modules. I mean, the theory of standard modules and is not yet, I think, there's not yet a theory for general gamma. So it's the level of representation. It is still problematic for general gamma. For finite type, it's been done, but that was a substantial work. But combinatorially, I don't know if there's any hope of getting better formulas. So Bernard, yeah, thank you very much. So that's something I would try to mention quickly towards the end of the talk, is that so projective modules have to do with canonical basis. Simple modules have to do with cluster theory to some extent. So so a number of dual canonical basis elements are actually given by cluster formulas. So that's somehow the best, yeah, thanks. Perhaps that's the best way, the best formula, the best things we have to compute these things is using this cluster theory when it does work. So it doesn't work for all simple modules.
Thank you.
All right, does anyone have another question for Raphael? Otherwise, we can start again.
Okay, thank you. So I will try to explain how one can first, I mean, prove that the canonical basis of Lucy coincides with within decomposable projective modules, and I will try to give you at least a quick algebraic way of understanding the PBW basis as having to do with standard modules. So it's something slightly easier, which are called proper standard modules. So I'll try to say a word about both. Okay, so let me switch to some geometry. So the geometry is very much, I mean, kind of a black box where you have a number of tools and you just apply them, and there isn't some there's very little true geometry going on for quiver varieties. When you use Lustig type quiver varieties, when you use Nakajima quiver varieties, then there is some more sophisticated geometry. Okay, so I will be assuming that gamma is Dynkin type, so most things generalize, but so what it does not generalize is going to the symmetrizable type. So we can do type AD using the geometry, but not type B or C or whatever F4. So we have now a quiver of Dynkin type, so we can look at representations of gamma. So representation of a quiver is the data of a family of vector spaces, finite dimensional vector spaces, and of maps given an arrow in the quiver. So each time we have a vertex, at every vertex we put a vector space, and for every arrow we put a linear map. So that now the beginning of the some of the relation between Dynkin type quivers and some of Lie theory is the fact that there's a bijection. So maybe I should say that the simple we'll call SI. So you put Vj equals delta ij k. Put k at vertex I and 0 elsewhere. And so now if you look at, so that means the K0, say, of rep gamma will be a free module with basis of simples. And if you look at indecomposable modules, there's going to be a bijection. There's a bijection from indecomposable representations of gamma up to isomorphism. So we can identify that with root lattice, where class of SI is a simple root. And now there's a bijection. So the indecomposable representations, if you look at the class in the Grothendieck group, this gives you a linear combination of simple roots, and you get exactly the positive roots. So the indecomposable representations of Quiver, I think in TAP, are up to the isomorphism parameterized by positive roots. And so now comes some of the groundbreaking. I mean, really paradigm in the theory, which was a work of Ringel, so which shows that not just the combinatorics of coming in Lie theory come in there, and also the Lie algebra itself, the Lie structure, or even the quantum version comes, and that's in the theory of Steinitz whole Ringel algebras. So it's usually called just whole algebra. So Ringel associates an algebra as having as basis so classes of indecomposable modules, and indecomposable up to isomorphism. And so we work over, we take representations over FQ. So now Q is not an indeterminate anymore, it's a prime power. And you can define an algebra structure. So again, there I'll be knowing powers of Q. So not here, but in the next result. So to multiply two classes, oops, sorry, it's not indecomposable, it's M representation. So let me, sorry, it's a basis. Multiplicative basis is what I said, but M is an isomorphism class of a representation of gamma over FQ. Sorry about that. So now, when we have two classes of representations, we can take their product as by looking at all possible extensions. So we sum over all representations up to isomorphism, and we look at the number of submodules n prime of L, such that n is isomorphic to n prime, and m is isomorphic to L mod n prime. So this times some of the class of L, so cardinality of that. So I use curly brackets to denote the isomorphism class of a module. So this makes an algebra, and Ringel's theorem is that we get the Lussig form of the quantum group, positive part, where the variable Q is now a prime power. Okay, so now Ringgold's whole algebra comes with a basis, and that's not the canonical basis. It would be it's too good to be true. So the basis of all representations is a so-called PBW basis, which has been defined in general by Lustig. I mean, this was before Lustig. Ringgold's work predates Lustig, and that's how Ringgold somehow proceeded to define a PBW basis. So you can understand your quantum group at least when Q is a prime power, and then Ringgold proved that those numbers here are actually polynomial in Q. So then you can recover the quantum group, not just its specialization. So I would like to say a few things about the PBW basis. So basic property of the PBW basis is a Poincaré-Birkhoff basis of the enveloping algebra of a Lie algebra is obtained by taking a basis of your Lie algebra and then taking monomials in that basis. But because the enveloping algebra is not commutative, you have to order the basis before you take the monomial. Okay. So PBW basis of the enveloping algebra of a Lie algebra requires an ordering of the basis of your Lie algebra. So here we do have an order on. So here I didn't even talk of monomials, but you'll see there are monomials and the basis. So our Lie algebra, the positive part, has a basis given by positive roots. So we need an order on positive roots, and the representation theory of Quivers gives us a basis. It gives us an order. I mean, there's more than one, but we can choose a total order. So the representations of a quiver, the category is so-called directed. So the Arcelon-Dehroiten quiver is a directed quiver. So there exists total order on phi plus. So maybe I'll call M alpha an indecomposable module corresponding to a positive group alpha. So there exists a total order on phi plus such that if there is a map from M alpha to M alpha prime, a non-zero map, then alpha is less than or equal to alpha prime. Okay. So we can number the roots. So phi plus to alpha n. Capital N is the number of simple root, the number of positive roots. And then we can now we can think of the M alphas where alpha is a positive root as being a basis somehow of the Lie algebra, and then we should take monomials of those. And indeed, if we take now M, so we take M to be a direct sum of indecomposable modules. So we take a decomposition, let's say M alpha 1 to the A1 copies. So if we take a general representation of the quiver, it will be a direct sum of indecomposable with multiplicities. And what one obtains, so there's a hop vanishing, but there's also next one vanishing. And because of that, the class of M, you can easily check, is going to be a product of M. So we take so that's almost what we want. It's almost the monomials. So we have to be just do one more step somehow. M alpha I, the class of this, is now I'm confused. I'm sorry. Somewhere I think I want to divide. I mean, I think I need to do. So there's just a slight subtlety in the PBW basis for Lustig's form of the quantum group. I mean, a PBW basis, normally you take a basis of your Lie algebra and you take monomials in those. So here we want to have divided powers with this form. So we need to take not just a monomial being a product of powers of our basis elements, but it's a power divided by a factorial or q factorial. So we do get so that the class of M is indeed a product 1 over A1 factorial n factorial M class of M alpha 1 star. There's a product. So we can describe a PBW basis element as a product.
You switched the order. You went alpha n to alpha 1 on the top line, and alpha 1 to alpha n. Does that?
Yeah, thank you. Yeah, so let me maybe rewrite that. So class of M is A1. So there's a big product where each alpha, for each I, we have to repeat the term AI times. But we've expressed our PBW basis element as a monomial in terms of the M alphas, which are in bijection with the positive roots. So there are the positive roots, okay? So the 5 plus parameterizes the basis of our Lie algebra G gamma plus. Okay. So we need to take all positive roots to get the basis of the positive part of our Lie algebra, and then monomials in those for a basis in the envelope. Okay, so right. So now we need to so now, I would like to tell you the shift theoretic version of Ringgold theory, which is Lustig's theory. So just one maybe last remark is that to define a PBW basis, all you need is to know how to multiply things and to know the PBW basis elements for associated to positive roots. Okay. So when we consider constructible sheaves, so what you look at is you look at the space of representations of your quiver, which is just an affine space. I mean, you fix the dimension vector, you fix the VIs, and you look at all possibilities for maps. So that's a big vector space. And you have to divide that by, you look at that space modulo, you look at representation modulo automorphisms. Okay, so you need to divide by a product of GL or general linear groups. Or you can, there's a geometric way of functioning that, it's called a stack. So you can look at the moduli stack, say, let me call it rep gamma, the moduli stack of representations of gamma. So maybe I should say, I mean, if gamma is just a dot, rep gamma is just a disjoint union of there's only one representation, a vector space dimension n for each n, but you have to take it modulo isomorphism, so you have to divide by GLN. So it will be point divided by GLN, something you will find as a sheet with brackets stack. So geometrically, this is not. I mean, there's basically no content. Okay, this is the content is more homotopical. Or you can think of point modulo GLN as being a simplicial object. Right. So so what Lussick does is it defines a product, a convolution, if you want, on constructible sheets, on the derived category of constructible sheets, by using a diagram, which is somehow the geometric version of what more geometric version of the counting that Ringel was doing. So you can look again at another stack, the one of exact sequences. So you look at exact sequences of representations of your quiver up to isomorphisms. They form a stack, and when you have an exact sequence, you have you can keep either the left term, the middle term, or the right term of the exact sequence. You have three maps, and so when you have two sheaves on rep gamma, you can pull them back to the stack of exact sequences. And then you can take direct image by R. This gives you a sheaf or complex of sheaves really happening in the derived category of constructible sheaves. And one thing that Lussick proves is that if F and G are semi-simple, or sums of simple perverse sheaves and sheets of those, this convolution will still be like that. And so you can define this category L, which is say the full subcategory of sheaves on this stack with objects being direct sums of shifts of simple perverse sheaves. So semi-simple perverse sheets and dual sheets. So you can use that as a graded category where the grading is just homological shift. And Lussick theorem is that if you look at the Grothendieck group as an additive category, this is UQ plus. Again, you get back your quantum group. And the point is that Lussick takes that as a definition of canonical basis. So it's not like Kashiwara who will define a global crystal basis, upper crystal basis as using a combinatorial method. Lussick's definition is geometrical. And so we have on the right-hand side a category, we take its K0. On the left, we have an algebra. And this algebra is a K0 of another category, which was built from Quiver Hecke algebras. And so for me, that was somehow the origin of the definition of Quiver Hecke algebras, was looking at Lussick's category and looking at X between simple and perverse sheaves, or certain perverse sheaves. And so we have the following theorem, which was proven indirectly by Michela Varagnolo, Eric Vasro, which is that this category U plus, this modular category we considered before, is so we should take I should say what I call GR proj. I'm sorry, is the same as L, and where projective indecomposable will correspond to simple varieties. So not only do we get that Lusik's canonical basis corresponds to classes of indecomposable positive modules, but there is actually this comes from a result at a categorical level. So we can use that so you can use that to and what we've seen before. So going back to Ringel, Ringel says that to define a PBW basis, you take elements of the whole algebra that corresponds to isomorphism classes of modules. So when you have M, somehow a representation of gamma, its isomorphism, it's going to give you a point, or I mean some kind of locally closed substack inside so you can write, you can say M is, let me write like that. You have XM, which is inside rep gamma. So it's it's going to be really a point modulo some group, and so you can take the constant sheaf on that locally closed subspace and extend it by 0, and you can now, so you can look at the constant sheaf on the XM. So it's not perversive. I mean, it's up to shift. It's going to be perversive, but it's not not a simple perversive anymore in general. And so you can. It's not going to correspond to an element in U plus GR proj, but it's going to be corresponding to something that's in more of a complex of those things, and it's actually a module. So this corresponds to what I would call maybe delta of alpha. So you can M is isomorphic to, as before, sum of alpha I a I, and we can put alpha to be this which is in z to the power 5 plus. So we have a certain, this is going to be a corresponding say representation of a Quiver Hecke algebra. Okay, so we fix, there's going to be some n, which is going to be the sum of the alpha i's, sum of the ai's, and delta of alpha is graded representation of Hn of our Quiver Hecke algebra. So you can define something which a priori is complex, but it has homogeneity only 1 degree, and it's certain graded representation. So Cato is the one who first considered this construction, I think. And you can decide that delta F alpha is going to be called a standard module. Okay. So the definition of standard modules like that is a little bit complicated. It comes from geometry. So that's not ideal. So if you remember how things were done, we could obtain so this, maybe I should say, by construction, the class of delta of alpha is going to correspond on the whole algebra side just to the basis element corresponding to M. So this will form, this is the PBW basis over O alpha. This is the PBW basis. So this gives somehow, this gives modules that for that gives a PBW basis. So that's good, but they're a bit complicated like that. So you can see that delta of alpha is actually isomorphic to, so same as before, to, maybe I should put it, I can put it. Delta of, so let me put a alpha n. AN, maybe you can put like that, star tensor product. So we can do the tensor product in our monoidal category. So that's, we're really dealing with representations of Hn of gammas for values n. Okay, so representation of HA1 of gamma, representation HAN of gamma. And we are, sorry, no, it could be bigger. So various Quiver Hecke algebras, and we're doing this tensor product, which is really some sort of induction procedure. And we can get our delta of alpha like that. And well, we can do as before, we can go one step further. Delta of alpha AI can be constructed as some sort of divided power where using the fact that there's a map. If we take a tensor power, or if we take such a module alpha I, delta of alpha I, which we haven't defined algebraically really, but we can get it as a divided power. So if we take tensor, if we take n copies of that. So if you take delta of alpha I and do this tensor induction n times, there's an action of this Quiver Hecke algebra, of this nil affine Hecke algebra Hn, and you can use that to define, to divide the side of your module by n factorial, by multiplying by the idempotent Bn. So the delta of alphas are very close to things you can compute, and that's the last type of basis. So we have simple modules, projective modules for Quiver Hecke algebras correspond to dual canonical basis and canonical basis. We have these standard modules, which are some of the more difficult ones to construct algebraically. I mean, it's not that the simples are easy to construct, but there is an easy definition of them, even if you don't have a concrete construction. So these you can construct more concretely, but it's a more complicated construction. And there is a last class of modules that's a little bit easier that you can define algebraically, the so-called proper standard modules. So the standard modules and the projective modules have a geometric interpretation. The simple modules and the proper standard modules don't have such a nice, simple, nice geometrical interpretation, but they have a quick proper standard module, quicker algebraic way of defining them. So there are modules that one called delta bar of alpha, where alpha is again a family, I mean, positive roots with multiplicities. And they are defined up to, again, a power of q by taking, reducing to the case of just one positive root. And here we just take powers. We don't have even to take divided power. So this comes, this is a tensor product in our monoidal category. So some induction of modules for Quiver Hecke algebras. And this is inspired by the formula that Rouquier gives to describe the dual PBW basis. So this will give the dual Poincaré-Birkhoff basis. So when you look at non-quantized enveloping algebras, there's just one PBW basis. When you look at the quantum version, you will have two bases which will be very close. They differ by just by polynomials in Q. One is just a scaling of the other by power of Q, but there are just two bases. And the idea is that the two bases are dual to each other for certain pairing on the quantum group. So we have this definition, and here now delta bar of alpha I can tell you what it is. This is just of L of alpha I. This is just a simple module. For a Quiver Hecke algebra where alpha is a positive root, if you write it as a sum of simple roots, and you take the sum of coefficients, this is the size of the Hecke algebra you're going to have to use. Okay, so taking simple modules of a particularly nice type, the one associated to positive roots, and tensoring them together in a suitable order gives you proper standard modules. Standard modules is a similar recipe, except that the module you start with, delta of alpha I, is there is a polynomial variable in addition, but there is so there's an action to be defined on this tensor product. Okay, so there is a subtlety there that makes you can define directly algebraically standard modules. So there are complications here. Is that I've chosen to parameterize things using positive roots and families of positive roots with together with a multiplicity, families of positive root together with a multiplicity. So that's good for from the point of view of whole algebras or geometry. But that's not the best algebraic way of parameterizing things. And the better algebraic way would be using a Kashiwara type parameterization where you would use the crystal. So you can parameterize the crystal basis by the crystal. So crystal basis coincides with the canonical basis. So it's somewhere it's parameterized by the crystal. But it's yeah, there are some non-trivial combinatorial things involved. And so all those things are yeah, part of the complexity of the algebraic theory of these combinatorial things. So one more thing I should say is that so we have four families of say graded representations of Quiver Hecke algebras. So we have the simples, we have the projectives, projective indecomposable, we have the standards and the proper standards. So the standard and the proper standard really depend on orientation of our quiver. It's the same as a PBW basis of Ringel. It's a basis of the positive part of the quantum group, but that does depend on the choice of an orientation, whereas the canonical basis does not. And we see it here. I mean, with again, the Quiver Hecke algebras themselves are independent of the orientation to isomorphism, and their simple and projective modules are independent of this. So the the structure you get there is that of so HN modules or graded modules is what it's some version of highest weight categories that has two. It's a version of highest weight categories where there are two types of standard objects, standard and proper standard, and that was formalized by Kleshev. It's called a polynomial highest weight category. So in the case Hn of gamma mod, so when we look at really Hn mod, so when gamma is just has only one vertex, then things are easier because L of alpha coincides with delta bar of alpha, and P of alpha is the same as delta of alpha. If I mess up. So in that case, if you remember the module category of nil affine algebra is the same as representations of a polynomial ring of your invariant polynomials. So it does not look very much like a highest weight category, but it is a polynomial highest weight category with just one simple one projective, and your standard and your standard, they coincide. And you see the delta and delta bars are very different. If you think of the polynomial side, one is your polynomial ring as a module over itself, and the other is just a field as a module over the polynomial. And that's a typical thing that you observe in general. So, so I've said a lot of things about some Dinkin type representation. So if you really want to do a representation theory of these algebras, in some sense, you want to define first what are the standard modules, which or proper standard module, which you can do if you can do it for positive roots, and then you take this tensor induction, and then you can actually parameterize the simple modules by saying those have a unique simple quotient, etc. So there is a way to get simple modules out of the standard modules like you would normally. Okay. So when you go via the geometry, things look a little bit different. So these constructions of so I don't know if I named the people, so I should maybe name the people. So it's what's it? Clash. The original work was Kleshchev, Ram. Then there is Kato, McNamara, and also Brendan. It's Kleshchev, Ram. So these are the people who have developed the theory, and the theory is only fully developed in the Dinkin type. So for more general quivers, it's still a problem to define algebraically proper standard modules, etc. And so gamma is just Dinkin there. Yeah. The last thing, last week I had planned to give a talk last week and one talk this week, so that I would have spent maybe a little more time. So I didn't want to shorten too much what I plan to do, but I want to say, to finish maybe with a remark that part of the theory can be extended in a fairly straightforward way. I mean, not easy, but in the affine case, so if you take, in particular, if you take gamma of affine Dinkin, so later I will explain. I will take here to be a Kronecker quiver, so I'll take type A1 affine. So this is a so-called Kronecker quiver, and it's indecomposable representations split there are varieties by different ways. There are some that have continuous parameter, and then there are two countable families of representations which are discrete, depend only on integer parameters. There's no parameter in the field, and one is called the pre-projective representations. And that's when you put k to the n here, k to the n plus 1, and as matrices, you take one of the arrow is this one, and the other arrow is that one. So you have a pre-positive representation that you can call B of n, where n is greater than or equal to 0. And you can look, you can do the whole algebra, or you can do the Lustig quiver variety by looking only at sums of V of n's. So it's a good thing to do because there are no self-extension between V of n's, number one, and two, if there is a non-zero map from an indecomposable representation to a V of n, that indecomposable representation must be pre-projective itself. And so you can look at substructure. So you can look at so the whole algebra. You get a whole construction which will give you the quantum group, which is the intersection somehow of say UQ of SL2 hat plus So that's what we have seen before, intersected with quantum group, I should say, of. Let me write it in terms of intersected with, well, you have a loop realization of, I mean, this is a loop algebra. And so you can look only at the loops with valued in SL2 plus. So you can look at only that part. And this is what you find. So the basis there, I mean, this is what do you want to say? How much do I want to say? I don't know. I mean, you have indecomposable representations are parameterized by non-negative integers, and so this will give you a basis of some for the Lie version of what I've written. So I should write it really. Intersected with SL2 plus. So that's actually just. I mean, this is a silly Lie algebra. It's just a C of. I mean, it's an I don't want to write too much as a Lie algebra because it's an abelian Lie algebra. It's misleading because the quantum group itself is not commutative. But you do realize like that the part of you look at the positive part from the Kac-Moody realization of SL2 hat. You intersect with the positive part somehow viewed from the loop point of view, and that's something you can realize geometrically in the whole approach using prepositive representations or geometrically using Lucy Quiver varieties. Okay, so you can look at the moduli stack of prepositive representation, and this will give you. This will be related to somehow part of the category U plus for Quiver gamma. So she's on the modular stack. So you can deal with representations with your Quiver Hecke algebras of type SL2 hat, or some of them, part of them, using just a stack of prepositive representations. And so what Peng-Chang will explain is that the geometry there can be related to another. So here we do constructible sheaves. So we can relate that to certain coherent sheaves. So on that side, what we see is something like the positive part of the Kac-Moody realization, and on that coherent sheaf side, we see the affinization on some of the loop part, SL2 plus. This is the affinization between. And so it's part of a general, so that's Shan Varnulo Pasro. So that's related to this. This was inspired by a result on the clusters work of Tony Licata and okay, I'm blank now. Second person. Sorry, I forget name. Which Shad Varnulo Vasco reinterpreted through work of Kang, Kashiwara, O, and others on realizing monoidal categorifications of cluster algebras using representations of Quiver Hecke algebras. So that's a topic of Quiver Hecke algebras. Inside, you can find some monoidal categorification of cluster algebras. Somehow that's underlying this picture. And maybe a last thing is that when you take your gamma, so you can look at constructible sheaves on rep gamma, and you realize something like this. So what we had worked on with Peng Shan, Eric Basfo, and Michael Vagnolo, which was looking at coherent sheaves on the cotangent bundle. To realize the affinization of this. And so this is in the sense of derived as a derived stack. So for gamma just a point, the stack is point modulo GLN, and this is something that will be discussed by Peng Shan next week. And this is okay. Somehow there is this is okay on K0 for gamma Dinkin, and that's work of Varagnolo and Basfo. So there is some more new chapter that has started, which is affinization of really categorical version of affinized Kac-Moody algebras using geometrically coherent sheaves on the derived cotangent bundles of Lussic's quiver varieties, quiver stacks. And this seems to be the right thing to do. For SL2, there is some very strong evidence. In general, there's evidence on K0. And some of the main question that's if not solved even for SL2 is to try to have an algebraic description of that side. So we want an algebraic. So we have Quiver Hecke algebras, and they should be affinized things which are some sort of affinized Quiver Hecke algebras, which would give endomorphism rings of objects that are not products of EIs, but products of generators in the loop version of the affine algebra. And these are more derived than the usual Quiver Hecke algebras. And so far, we don't have an algebraic description even for SL2. So I'll stop here. Thank you.
Thank you very much, Raphael. Let's please thank our speaker. Wonderful. Does anyone have any questions?
I have a question. I have two questions. First is whether this algebra can give some not invariant. I mean, for example, can it recover Jones polynomials or anything we know before? Thank you.
So yes. So the answer is yes, using a generalized version of Quiver Hecke algebras, which were introduced by Webster. So you can think, I mean, not Quiver Hecke, of cyclotomic Quiver Hecke algebras. So Quiver Hecke algebras are associated to choosing a quiver. If you choose in addition a weight, a dominant weight, you can define a certain quotient of that algebra, which is called a cyclotomic Quiver Hecke algebra. So now, when you want to look at not invariants like Jones's invariant, you're thinking of taking colored versions of taking a tensor product of simple representations. And so you would want algebras parameterized not just by one weight, but family of weights, and that's something that was introduced by Ben Webster. And Ben Webster proved that indeed you do recover a number of classical categorified not invariants using these algebras. So what one can do is introduce some sort of hop structure on that category, U plus, some sort of coproduct, and so to get not invariants or more invariants, one needs also some sort of a braiding and some compatibilities, and that's still difficult because that can be done partly for GL11, but Kac-Moody case is harder. So going to cyclotomic Quiver Hecke algebras, choosing a weight is analogous to geometrically going from Lustig's Quiver varieties to Nakajima Quiver varieties. So thanks for the Eugene for the work.
Okay, thank you. And probably another question is because we know Quiver Hecke algebra is by its geometric explanation, can we use something similar to Springer theory to classify all the simple representations?
So say it again. You want to use
something similar to Springer theory to classify all the simple representations.
I mean, you can use so it would be more for cyclotomic Quiver Hecke algebra. So you can use Nakajima's theory, but what it does is it's going to have to do with representations of affine Kac-Moody algebras or affine quantum groups. I mean, the Springer theory developed by Nakajima is the role of the Weil group is replaced by a quantum group. Okay, so it's not helping with representations of Quiver Hecke algebras. Quiver Hecke algebras are not they don't arise quirk like affine Hecke algebras or whatever, affine Weil groups or Weil groups. They arise slightly different manner. So so using a Springer theory there, it's very much like type A. So it's a case where Springer theory would not be as deep, I suppose.
Okay,
so,
thank you.
Yeah, one thing I wanted to say is the names. So the Quiver, the cluster theory I was referring to is Sabine Kautis and Howard Williams. I'm sorry, I mentioned Tony, but that was that was not the right people.
Thank you. Does anyone have any more questions? All right, in that case, I'm going to stop the recording and let's thank our speaker one last time. Thank you so much, Raphael, for a fantastic talk.